Good morning, everyone, and thank you for joining us today. Welcome to Megger's monthly webinar series. Today's topic is an insight into differential protection scheme for different applications. My name is Sarah Bauman, and I'm the Marketing Programs Manager for Megger NAFTA. I'll be acting as your moderator for today's presentation and supporting you on any technical issues or questions that you may have for our presenter. On the right side of your screen, you'll see a control panel, and it kind of looks like this one here on the right. You can submit any questions at this time or throughout the duration of the presentation by typing in the box highlighted in red. And I'll read the questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive one NETA CTD and one PDH or 0.1 CEUs for attending. You will receive an email within about 2 business days after the webinar, and that email will also include a copy of this PowerPoint presentation, excuse me, and a link to the video recording of the webinar if you'd like to watch it again, or you can share it with your colleagues. So again, you can ask questions at any time on the right-hand side. And today's presenter is Vijay Sundaram. He's a Megger Applications Engineer. Okay, let's go ahead and get started. Thank you for joining us today, Vijay.
Thank you, Sarah. I appreciate it. Good morning, everybody. My name is Vijay. I'm the Relay Application Engineer. Today, the topic of discussion is going to be differential protection and its applications in different segments of the power system. I have divided the presentation into 3 sections. The first one is talking about the fundamentals of differential protection. The second section is where I talk about how do we use the differential protection idea in protecting different assets of the power system, like generators, transformers, transmission lines, motors, bus bars, reactors, whatever it is. So how do we use the differential protection concept in protecting the assets? The third section I want to focus on is how do we test or how do we validate that schemes that we implement to protect transformers, per se. So there are 3 sections. The first one is going to be about fundamental. So the whole idea of differential protection starts from Kirchhoff's current law. So if you look at the circuit shown in that screen right now, you have a voltage source, and that voltage source is connected to 2 resistors which are in parallel. And you have the current IS that is flowing through the circuit from the voltage source. I can say that the current through the resistor is I1 and the current that is through the resistor 2 is I2. According to the Kirchhoff's current law, what it says at any point on the circuit, it could be a node or it could be a junction or any point in that circuit, the sum of all the currents that is flowing into that point is equal to the sum of the currents that is flowing out of that point. So mathematically representing, in this case, IS will be equal to I1 plus I2. So this is the concept of the differential protection, Kirchhoff's current law. So everything that comes in should have to go out. So we can extend the same concept to any equipment in the power system. So what I have mentioned there is just a generic name called equipment. It could be a generator again, it could be a transformer, or it could be a transmission line, or it could be a bus bar, it could be a motor, it could be anything else in the system. So let's assume that the current that is flowing through that equipment is I. So I coming in, I going out. So if I put 2 CTs across that equipment, as shown, CT1 and CT2, and you can also notice that the polarities are different in this case. And if I connect that across the equipment like this, and let's assume that the current that is going through is I1 and I2 on that circuit. And if I put a coil across it, let's say the name of the coil is operating coil, and the current through that is IOP. So the current through that coil will be equal to the difference between that current, right? According to the Kirchhoff's current law, it will be the difference between the current I1 and I2. In ideal world, it will be 0. There should not be any current that flows through that operating coil. So when an external fault happens in the system outside of the protected zone, one thing to notice is in a differential protection, the zone is defined by the CTs. So anything outside of the CT protected zone, we call that as out of zone. So if there is a fault outside of the zone, the current through that equipment still doesn't change. So the CT1 and CT2 pretty much sees the same current as it was before the fault as well. So the directionality of I1 and I2 will not change, and the current through the IOP will be still the difference between I1 and I2, which will be 0. So for an external fault or for a normal operating condition, the current through the IOP, the operating coil will be 0. What happens if there is an internal fault in the system? When there is an internal fault within that equipment, so this internal fault could be, a winding insulation problem, or it could be a fault within a transmission line, or it could be a fault on the bus bar of the power system. It could be any fault within that protected zone of protection. What happens then? Then the system needs to feed the fault. So the directionality of CT2 current changes here, like it is shown. Now, for an internal fault, the current that is flowing through the IOP, which is the operational current, will be addition of I1 and I2 according to Kirchhoff's current law, right? So for an internal fault, that operational current that is flowing through the operating coil will be more than 0. So that will make the relay operate and trip the breaker. In general, the basics of differential protection, the ANSI number associated with the differential protection is 87. So when somebody says it's an 87 function, what it means is it is a differential function. Usually it is associated with the alphabet after that as well. For example, an 87G. What does that mean? It's called the generator differential protection. 87D, transformer differential protection. 87M, motor protection differential, motor differential protection. 87B, which is a busbar differential protection. So it's an easy way to know what we are talking about. Typically, the differential protection in general is a very sensitive function, or it's a highly sensitive function. What it means is even any fault within the zone of protection, the differential protection is going to pick up, and it is going to operate on it. So it is going to be a sensitive protection in your system. Most of the protection systems that involve differential are primary. So your differential protection will be your primary source of protection in the power system. It is also selective. What it means by that is the differential protection operates only for the faults within the protected zone. It will not, or it should not, operate for the faults outside of the protected zone. And most of the time, it is an instantaneous operation. There is no intentional time delay associated with that. The reason for that is because when there is an internal fault in your transformer, you don't want to feed the fault for too long, then you might damage the internal parts like the windings of the transformer, which you don't want that to happen. So you need to clear the fault immediately. So typically the differential protection is an instantaneous function. There is no intentional time delay associated with the protection function. Having said that, there are multiple factors which affects the normal operation, which affects the selectivity and also the sensitivity of the protection of the differential protection. For example, you can have two CTs, as we mentioned before. You can have two CTs, the CT1 and CT2. It could be from the same manufacturer with the same CT ratio and same material, but it may not have the same exact operating characteristics. That might cause current mismatch on the secondary circuit, thinking that the relay will think that it is an internal fault. So the CT characteristics play a very important role in the normal operation of a differential function. In real world, the operating current is not always equal to zero. It is pretty close to zero during a normal operating condition, but it is never actually equal to zero in a steady state condition. So that is one of the reasons why typically the protection engineers use percentage differential. So what does percentage differential mean? If you look at the picture here, or if you look at the circuit here, you will notice you also have two resistors that are connected in that circuit. So it is called restraint coil. The one which is horizontal, those are horizontal, are called the restraint coils, and the vertical ones are called the operating coil. So when there is an external fault in the system, again, the current through that equipment doesn't change. So the current seen by the CT1 and also CT2 will not change. And hence the directionality of I1 and I2 is pretty much the same. If I assume that the current through the resistors, the restraint coils, is IR1 and IR2, for an external fault, the operating coil current is far weaker than the current through the restraint coil. So typically for an external fault, you would expect the differential protection should not pick up because the restraint current is far greater than, or the strength of the restraint current is far greater than the operating current. On the other hand, when there is an internal fault within that protected zone, then the system is going to feed the fault. And the directionality of I2 changes, which causes the current to flow through the restraint coil and then through the operating coil as well. So in this case, the current through the operating coil will be far greater than the currents through the restraint coil. So the relay will operate for that. Now, when we talk about percentage differential, we always talk about a graph. It is a graph between the restraint current, which is IR on the x-axis, and IOP on the y-axis. So if I draw a graph between the IOP and the IR, typically the IR, the calculation for the IR depends upon the type of manufacturers. Different manufacturers use different calculation methods. I have presented here some of the most common calculation methods. It could be the magnitude addition of the currents through the two restraint coils, or it could be an average of that, or it could be divided by 3 of the currents that is going through the two restraint coils, or as you see here, it could be greater of the two, or it could be lesser of the two as well. So if I have a slope here, what does that mean? As an engineer or as a technician, what does that mean to us? So at this point, let's assume at this particular point, you at least need 50% of whatever the IR is for the relay to operate. So your IOP should be 50% or more than IR at that particular point. Taking this slope concept and implementing it for different applications is the most it's one of the complex things in the differential function. So instead of going with one slope, like 50% or 20% or 30%, we can have a combination of the slopes. So as explained here, this part right here is for the minimum pickup. The reason why we have this minimum pickup is pretty simple. I mentioned to you about the CT mismatch, two CTs, even though from the same manufacturer, same type, and also the same ratio, it still will have different operational characteristics or slightly different operational characteristics. That will cause the current mismatch on the secondary circuit. So to minimize the relay from picking up those CT mismatches caused by the CT ratios, you need a minimum pickup. So this part right here prevents the relay to operate based on the CT mismatch. current. And then you can have a slope 1. The typical value of the slope 1 is about anywhere between 10 to 25%. And the slope 2 value will be somewhat in the range of 40 to 50%, or somewhere around 35 to 50%. The reason for the difference in the values between slope 1 and slope 2, especially the slope 2, is for you to prevent the relay from operating when there is a heavy fault on the system, which causes higher currents to flow through the system. When the currents flowing through the system is high because of a fault, the probability of CT saturating is high, because in the power system, most of the CTs are typically operated pretty close to the knee point, and when the excitation current changes because of the fault, then you are pushing the relay into the saturation region. So you don't want the differential relay to operate for a higher fault. So that's one of the reasons why you have a higher slope, especially the slope 2. So when the calculated value or the measured value of IOP and IR falls in the region above the graph, it's called the operating region. And if the value falls anywhere in that region, the relay is going to operate. If the value is less than that, it is going to fall in the restraint region, and the relay will not operate. So this is the basic of a percentage differential protection function. Now, so far, I talked about currents, comparing the currents in the secondary circuit of the CT. There is another option of doing a differential function with voltage. So in this case, the high impedance differential protection is characterized by having the impedance of the relay really high, which is denoted as ZR. So the impedance of the relay is really high compared to the impedance of the CT here. So what happens is, when there is a fault, because of the really high impedance of the relay compared to the overall impedance of the CT and also the lead that is connecting into the relay panel. So if I take the junction resistance along with the impedance of the relay, if I take the impedance of the relay along with the junction resistance and compare that with the CT impedance and the lead resistance, the CT and the lead resistance will be really low. So all the fault currents flows through the CT instead of flowing through the relay. So what we are doing in this case is we are measuring the voltage drop that happens across the relay, and the operation is based on the value measured across the relay. So if it is beyond, or if it is less than a threshold value, which is typically for an external fault, so if the voltage value is less than the threshold, then the relay will not operate. But if the voltage measured across the relay is higher than a threshold, which typically is for an internal fault, the relay will operate. To summarize, the high impedance differential, in a high impedance differential protection function, the impedance of the relay is really high, which forces the differential current to flow through the CT. And in this protection function, we are not monitoring the difference between the current, but we are monitoring the voltage. So if it is above the threshold, the relay will operate. If it is below the threshold, the relay will not operate. And if there is a fault, a close-in fault on the equipment that we are trying to protect using high impedance differential, if there is a close-in fault, the voltage that appears across the CT will be as high as the open circuit voltage of the CT. Since that is connected directly to your relay, you don't want to damage the relay with high voltage. So what you do is you put a variable resistor, which is called a varistor, right across the relay circuit or the relay input, which prevents any damage to the relay from high voltage levels. Now, in this protection method, the CTs are connected in parallel with each other. And typically, all the CTs will have the same ratio, and they are used at the full tap of the CT. So, in summary, we talked about the basics of the differential protection. We also talked about what a percentage differential protection is. We talked about the slope characteristics, why we have dual slope or multiple slope, and we talked about high impedance differential function. I hope that should provide a comprehensive explanation on the basics of differential protection. Now, let's talk something about the applications. How do we implement these protection schemes in order to protect the assets of the power system? Let's start with generator differential, which is typically 87G, called as 87G function. The basics of the generator differential protection function is pretty simple. What are we protecting in the generators using the differential function? Mainly, the differential functions are used to protect the stator windings. You also have other protection functions to protect the stator, which are known as the stator ground fault, calculated 95% stator earth fault and 100% stator earth fault protection. But we are not going to talk about the other protection functions. We are going to talk about the differential functions for the generators. So typically they are used for protecting the stator windings, and these differential protection offers prevents the phase faults. As shown in the circuit here, you have three generator windings or stator windings. You have the neutral side and also the phase side. Typically, the differential function CTs are connected between the neutral and the phase side. And each phase is compared separately in order to determine if there is a fault on A phase, or B phase, or C phase. In a generator differential, when you're implementing in a generator differential, you typically have the CTs will have the same ratio. It will be of the same type from the same manufacturer most of the time, mainly in order to minimize the mismatch current. Also, you have the burden of the CT and its circuit is kept typically low. Majority of the time, percentage differential is what is implemented, and the slope is about 10 to 25%, as I mentioned before. The slope is about 10 to 25%. On top of that, depending upon the type of generators, you can also have a high impedance voltage differential as an option. Typically, when the generator differential operates, it's an instantaneous operation. If on a generator, typically, the trip signal is called Class A trip. What does that Class A trip mean? When the relay issues a Class A trip, it pretty much opens all the breakers associated with the generators. It also removes the field supply, along with reducing the prime mover or removing the prime mover into the system as well. So a Class A trip will pretty much disconnect the generating station, or at least a major chunk of the generating station, or at least the generator, from the power grid. Now, let's see what some of the challenges that is. We talked about a lot of factors that prevents the normal operation of a differential function. One of those challenges is called recovery inrush. What does that recovery inrush mean? The differential relay should have good immunity to avoid incorrect operation on an external fault that significantly lowers the voltage, where the voltage recovers when the fault is cleared. So For an external fault, you don't want your differential relay to operate. So because of some faults outside of the protected zone, which is the phenomenon is called the recovery interest, you don't want the differential relay to operate. If there is no fault in the system, but you're trying to charge your transformer, when you are charging a transformer, it usually takes the magnetizing current through it. And the magnetizing current is of a very high magnitude, and we're going to talk about that in the next few slides. So those kinds of magnetizing currents, which are typically called as the magnetizing inrush or switching currents, typically the generators which are connected to the system is what is feeding those magnetizing currents. So the generators will also feel that inrush current. So the inrush current typically is of two types. One could be because of the fault, or it could be of some equipment switching. So you don't want the generator differential protection to operate for those kinds of conditions. The other problem is asymmetric CT saturation. When there is an external fault in the system, a pretty close-in fault to the generating station, the fault magnitude will be really high, which could typically saturate either the neutral side of the stator or the phase side of the stator. So it could saturate any of these CTs. So when that saturation happens, the response from the CTs will not be true. So if the response from the CTs are not true, or not exactly the reflection of the primary values, then you cannot trust the outcome of the protection function, which depends on the CT outputs. So when this asymmetric CT saturation happens, because of a fault external to the system, your differential protection may get affected because of it. The other factor that could cause the asymmetric saturation is because of the presence of DC current in the system that could be from the generator characteristic itself. On top of that, some of the other challenges faced by the generators are during startup condition, your differential relay should have a wide operational frequency range, anywhere between 10 hertz to 80 hertz. So you have a wide range to cover for the differential operation, or the CTs has to cover a wide range of operational frequency. These are some of the challenges for the normal operation of the differential function. How do we overcome this challenges, and how do we implement those differential schemes that we talked about? So one thing that we mentioned is high fault current. So if there is a high fault current, typically we can use the CTs with a very high knee point value. So the CTs will not saturate for the high fault current. On top of that, you can also use the percentage differential protection with multiple slopes, as we mentioned before. So you can have multiple differential protection functions. The other option is to use a high impedance voltage differential. I see that there are lots of questions coming on to define what a CT saturation is. I don't have a clear picture of how a CT saturation will look like, but let me see if I have a pen or something like that. I don't think I can draw anything here, but I think I'll come back to the question later. So the typical settings that you will see on a generator differential are, the winding pickups, the pickup value of the windings, the time delay associated with the differential operation. This is an intentional time delay for the operation, mainly for time coordination purposes. And it will also have the slope characteristics, which is, what is the minimum pickup, what is slope 1, what is slope 2. On top of that, you also have the restrained and unrestrained pickup values. So these are all the settings that are associated with the These are all some of the settings that are associated with the generator differential function. In the section number 3, we will see how to test or how to validate these settings and the procedure to test them. Now let's talk about the transformer differential. So this might be one of the most complicated differential protections in power systems. The underlying concept of transformer differential is very simple. You have the amount of the current coming in should be equal to the current coming out of the transformer, right? So you will have CTs connected on the primary side and also CTs connected on the secondary side, which compares the current in that particular phase. You know, A phase compares primary and the secondary currents on the CT circuit. But the differential function, which typically protects the transformer windings, which also provides protection for both the phase and the ground faults of the transformer, faces a lot of challenges. I have tried to come up with the bullet points on all the challenges faced by the transformer differential. I am going to take my time to cover each and every single challenges and how we rectify it as a protection technician or a protection engineer, how we rectify this in the field. The first challenge is current mismatch. We talked about the current mismatch a little bit before. You know, you have two CTs, but you know, even though it has the same CT ratio, same tap, and same manufacturer, same type, it will still have different operational characteristics. So the response from two CTs will be a little bit different. The response from the two CTs will be a little bit different, and that will cause a current mismatch. The other current mismatch might be caused by transformation ratio. Because we are talking about a transformer typically have, you know, 115 to 230 kV or 230 kV to 115 kV. So that transformation ratio will cause current mismatch as well. On top of that, if you use load tap changes for voltage regulation, again, you're dynamically changing it using the on-load tap changer, or you have a fixed tap using the no-load tap changer. In those cases as well, you will have current mismatch. The second challenge that is in the system is because of phase shift for a delta Y transformer or Y delta transformer. The type of connection that I wanted to show in this here, or that I've shown here in this transformer, is YY, but you can also have a delta Y transformer or Y delta transformer. Typically, the high side leads the low side by 30 degrees, or if you're from a different part of the world, the delta side leads the Y side by 30 degrees. So you have that phase shift associated with the current that is being measured by this relay from the CTs across primary and secondary. So the third challenge could be because of the magnetizing inrush current. Typically, when you charge a transformer, a good amount of current is taken by the excitation path of the transformer, and that current magnitude is about 5 to 20 times the nominal value. So when you charge the transformer, the system will see about anywhere from 5 to 20% of the nominal values. That's only for a short duration. It is not for a prolonged period. So like the one that is shown here, so your inrush current will be really high compared to what the supplied voltage is, but that's not forever. It has a decaying DC component as well, depending upon the DC constants of the generators that is the transformer is connected to. So the inrush current will be really high. What happens if the inrush current is really high? That is being seen by the CTs that are connected to the differential protection. So if the inrush current is really high, the CT may saturate, and when the CT saturates, the response from the CT may not be the true reflection of what is happening in the primary side. That could cause different results from what we are expecting from a differential operation. Or, in other words, the differential operation might not be reliable during the inrush condition. So how do we implement or how do we overcome this challenge? We will see that in the upcoming slides. But some of the other challenges are overexcitation. The overexcitation typically happens to the transformers or to the transformer differential that are directly connected to the generators. Generators could be unit generators, or it could be direct generators which are connected to the breakers directly, or there could be a generation transformer that is a step-up transformer that is connected to the generators as well. So overexcitation is the challenge that is typically faced by the transformer differential that are connected to the generators. The other thing that we already talked about is CT saturation, which could be caused by an external fault as well, not necessarily by an inrush current. The other thing is presence of harmonic contents. The harmonic contents that are present in the inrush current and also the overexcitation condition can cause the CT to saturate if the DC levels of the waveforms are higher. So the harmonic content will also be a challenge to face when you implement a differential function. The other challenge that I could think of is the zero sequence current. So for any external ground fault, especially for the Y-type connection on the transformers, you will also experience, or the relay will also experience, a zero sequence current. So how do we mitigate those challenges? Now let's first take an electromechanical differential relay or electromechanical transformer differential relay. How do we mitigate the CT mismatch? Give me a second. So the CT mismatch mainly caused by the CT ratio. So you can select the CT ratio based on the transformer ratio or the transformation ratio of, so in this case, the transformer ratio is 2:1. And also, you have to make sure that the delta connection increases the value of the phase voltages or currents by 1.732 factor. So you have to consider that as well when you're calculating the CT ratio of the differential function. So in this example, the CT1 on the primary side have 5:1. Excuse me. And you have on the secondary side, you have CT, which is 1:1. And the current through that is I capital A dash. And on the secondary side, you have I small a dash. So when you're calculating the CT ratio, this will be the equation that you can use for this particular example. So you have to select the appropriate CT tabs on the primary side and the secondary side based on the transformer ratio and also the type of transformer connection. Considering only the electromechanical relays, phase shift again is another problem or another challenge faced by the differential protection. If you look at this picture, you can see the transformer here is connected delta Y. So one of the techniques that you can use to prevent the phase shift and also to prevent the transformation ratio with the delta side being 1.732 times higher than the Y side, you can connect the CTs of the delta side of the transformer. You can connect the CTs in Y, and the Y side of the transformer, you can connect the CTs in delta. That way, you are mitigating not only the phase shift, you are also preventing any zero sequence currents, which is nothing but the current through the neutral, the grounded point of the transformer. So you will also prevent the zero sequence current taking effect into the secondary circuit, because the Y side which takes the neutral current, the CTs are connected in delta. There is no way that the neutral current will flow through the delta connected CTs on the secondary side. Similarly, there is no zero sequence current on the primary side, so you will not see that on the primary CTs as well. How do we do these two, or actually three of these? One is the current mismatch because of the transformer ratio and the type of CT connection, or sorry, the type of transformer connection, phase shift, and also zero sequence. So there are three challenges. How do you rectify these challenges in a microprocessor relay? So typically, all these are internally calculated in a microprocessor relay. So you would enter these values based on the settings of the transformer. You would enter the values and also the settings of the relay. And based on the settings, the microprocessor relay calculates all these, what is known as compensation factors. So you have three-phase compensation factors, single-phase compensation factors, zero-sequence compensation factors. You have all these compensation factors, which pretty much calculates the same way how an electromechanical relay would do through connections. So these internal compensation factors will take care of the CT mismatch, phase shift, and also zero sequence elimination. I could not cover the calculations of how the transformer differential relays, especially the microprocessor ones, does the compensation factor calculation, but it will be a presentation on its own. When we probably in the next webinar or so, if we come up with the topic of transformer differential protection, we will have the time to go through the calculations behind it. But if any of the listeners are interested in knowing the calculations behind it, please let us know and we'll try to give you the answer offline. Now, the other factors like magnetizing inrush, you have magnetizing inrush, you have overexcitation, you have CT saturation, harmonic contents. How do you overcome those things? So we talked about magnetizing inrush, not so detailed, but a little bit about the magnetizing inrush. When the magnetizing current, when you charge the transformer, and during the transformer charging, you will see high amount of current that is flowing through the transformer. The high current or the inrush current is being supplied from the nearby generating stations if it is connected to a generator, or from the grid itself. How do I differentiate the inrush condition from an external fault condition, or from a normal operating condition? Typically, the differentiation is on the harmonic content of the waveform. So you can have separate filters on the relays which filters out harmonic contents. When the transformers are charged, the even harmonics are pronounced more. What I mean by that is, the second harmonic or the fourth harmonic will be the content of the magnitude of the second harmonic, and the fourth harmonic current waveform will be higher during transformer charging. So if you have separate filters for an electromechanical relay I'm talking about, if you have a filtered circuit, The filter circuit can be tuned to 120 hertz on a 60 hertz system or 100 hertz on a 50 hertz system. So you can tune the filter to that particular value and you can measure the amplitude of current for 100 hertz. That will be your second harmonic amplitude. So if you have second harmonic and fourth harmonic, depending upon the design of the system, but let's focus only on the second harmonic for now. So if you have second harmonic and also the fundamental current is higher than the threshold value or the pickup value, then typically you can issue a block signal or you can prevent the relay from operating during that condition. Because of the primary or the fundamental current higher than the pickup value of the relay, your relay will trip. But you also have as a relay, you are also seeing the second harmonic or the fourth harmonic or both, second and fourth. So you will say that, okay, now I'm seeing the second harmonic and also the fundamental being high. So this means that it is an inrush condition. For an inrush condition, as I told you before, it is only for a short duration. It is not for a very long period of time. So you would let that pass through by blocking the operation of the relay. So this is called harmonic blocking. So the magnetizing inrush can be mitigated, or the relay operation for magnetizing inrush can be avoided by introducing a block function, or also known as, we can also restrain the operation of the relay when you see that. So that will be called harmonic restraint. When you block the operation of the relay, it is called harmonic blocking. So here is a graphical representation of how the microprocessor relays will see the second and the fourth harmonic values. So as you can see, the DC component is high for an inrush condition. The fundamental component is higher than the pickup value. You also, on top of that, you are also seeing the second and the fourth harmonic. So when the relay sees that, the relay determines, okay, so I'm seeing a lot of second harmonic, more than what it should be for a regular operation. So this must be an inrush condition, and the relay will restrain itself or block the operation of the differential function. Now let's talk about overexcitation. Just a minute. So overexcitation typically occurs because of the volts-hertz increase, V by H. The reason for the V by H increase is mainly because there could be a load rejection in the system, and the load could be significant, and that will cause the voltage to increase where the frequency is pretty much staying at 60 hertz. So the volts per hertz will increase in the system, and that will cause the CTs to saturate. The way to overcome that overexcitation condition is similar to what we saw in the magnetizing inrush, which is the presence of odd harmonics, which is the third and the fifth harmonic. So the same way we implemented the harmonic blocking or harmonic restraint function for the magnetizing inrush condition, we can have the same thing for overexcitation condition as well. The other things like CT saturation. The CT saturation could be caused by close-in fault or an inrush condition, or it could be caused by an internal fault or a remnant flux that could cause a higher fault current or higher current amplitude of current in the system, which could drive the CT into saturation mode. So in order for you to overcome that kind of problems, especially the close-in fault, the inrush condition, you can use multiple slope differential, the percentage differential, to prevent relay misoperation. Okay, so now let's, I think I have about 10 minutes left, or maybe 15 minutes left. So I will go through the rest of the presentation as quick as I can, but pretty much the concept remains the same. Let's talk about the bus differential here. So for an external fault, so here is a bus, and there are one feeder, actually 4 feeders in here. For an external fault, so all the feeders are feeding that fault here. So the direction of the current is as shown. I1 is into the bus, I2 is into the bus, I3 is into the bus. But the I4 is away from the bus. In this case, I4 will be equal to I1, I2, and I3. So overall, if you look for an external fault, the amount of current that is coming in, which is I1, I2, and I3, will be equal to the amount of current that is flowing out of the bus, which is I4. On a bus differential, the CTs are all connected in parallel. So this way, it will see all the flow of current in this particular direction as mentioned in the diagram. On the other hand, for an internal fault, if the fault happens on the bus, now I1 is feeding that fault, or the feeder 1 is feeding that fault, I2 is feeding that fault, I3 is feeding that fault, I4 is feeding that fault. So the amount of current that is flowing in will not be equal to the amount of current that is flowing out. And this will be detected by the CTs, which are connected in parallel, and the relay will operate for that. So in a bus, typically the high impedance differential function is implemented, and that will prevent, and also the external resistor or the varistor that I talked about will prevent any high voltage that appears across the relay contacts. In a bus differential, the CTs may have the same ratio and type, and all the CT, as I mentioned before, the CT terminals are connected in parallel. The high impedance voltage differential is mostly preferred as well, mainly because of the fact that when there is a fault on the bus, the fault current will be really high. So the CT saturation and all those effects that affect the differential operation, we don't want to deal with all those things, so we are going for the voltage differential. Having said that, you also have the option of incorporating the multi-strain or the multi-slope current differential method as well. Now let's quickly talk about the line differential. So you have a transmission line like this, and the CTs are looking at in this direction. So when there is an external fault in the system, the current flow through that transmission line is as shown here. So since the comparison happens through the pilot wire, the relay will not see any differential current, and the relay will not operate for an external fault. On the other hand, for an internal fault, the relays will see a differential current on either side. So the current from the remote side, let's say this end is your local, and this end is your remote. So the current and voltage as seen by the relay associated with the remote end will be sent to the local end through a pilot wire. And the current comparison happens in each of these relays. So the voltage and current measurements that happens in the local end is also sent to the remote end through the pilot wires, and the current comparison happens in the remote end as well. If there is a difference of current between these two ends, then the relay will operate immediately. Typically, the percentage differential is implemented to compare the currents that is from either end of the transmission lines. Finally, I want to talk about motor differential, but motor differential is pretty much similar to the generator differential that we discussed earlier. In this case, the differential function protects the windings of the motor, typically the stator windings of the motor, and it provides phase and ground fault protection. In the motor differential, the CTs will pretty much have the same ratio and same type in order to prevent the mismatch. But we did cover completely about the CT mismatches and the other challenges faced for a generator differential, which can be applicable for the motor differential as well. Now let's go to testing. So testing these protection schemes, what do you do when you're testing the protection function? Well, validating the protection scheme is pretty important because, as I mentioned during the start of the webinar, I mentioned protection function is pretty much the primary function. Differential function is pretty much the primary function, protection function in generators or transformers or bus bars. So you need to validate the settings of the relay to make sure the relay operates for in-zone faults and it does not operate for out-of-zone faults. If the relay operates for an out-of-zone fault, then pretty much you are compromising the stability of the power system. You don't want to do that. So you need to validate the protection schemes. On top of that, let's take transformer for example. If you have an internal fault in a transformer and you're not clearing it soon enough, those undetected internal faults could cause serious damages, permanent damages to the windings of the transformer. I don't have to tell you how much a transformer costs, definitely in the millions of dollars. So you don't want to damage the transformer because of an uncleared, even though a small magnitude fault. You don't want to do that. So you really need to test the system to make sure the settings are fine. Now there are two schools of thoughts on that. Do I test single phase or do I test three phase at the same time? Typically, when you're dealing with electromechanical relays, you test one phase at a time. So it might be a single phase test that you might perform because a phase will have a certain either a Westinghouse or an ABB Westinghouse or a GE relays in the system. So you have single phase covering for one, either A, B, or C phases. The modern microprocessor relays, on the other hand, can take all the three phases at the same time. Sometimes for bus differential or bus protection, you have more than three, because you have if you take A phase, you have 3 or 4 feeders, so you have more CT inputs coming into the relay. So taking that topic beyond the single phase and three phase, the chain of thought will be, do I test only the differential element, or do I actually test the whole scheme? Especially when you're testing a bus differential scheme, you need to provide all the CT inputs into the relay at the same time for it to see a fault either on A phase or B phase or C phase. So that becomes challenging when you start testing the differential function. So there are two things. One, either do I do a single phase or three phase? Or do I do an element testing, or do I do a scheme testing? For single phase or three phase, if it is a microprocessor relay, depending upon the settings of the relay and the logic implemented in the relay, it is recommended to do what the logic dictates. If the logic dictates single phase testing or single phase tripping, then you test single phase. There is no harm in testing single phase. If it requires all the three phases, then you need to have three-phase system. for testing. On the element and scheme testing, it is entirely up to the utility or the governing body to determine whether they need to mask the other elements when you're testing a differential function, or do you want to do a scheme test based on the settings of the system, which obviously requires a lot of knowledge or understanding of the scheme that is being implemented, and the technician who is testing it or the engineer who is planning on testing it should have a deep knowledge of understanding of the system or the scheme. Now, what are all the tests that is done for a protection scheme or a differential protection scheme? The first is through fault or an external fault test. There could be winding pickup test and a time delay test. The other thing that you can test is a characteristic test or the slope test. Along with that, you can also do a harmonic block test. I think we discussed about that previously as well. So you have a harmonic block test or a harmonic restraint test. I will cover each and every single procedures in detail. All these are secondary injection methods. I'm not talking about primary injection in these testing. I'm only talking about secondary injection where you take a test set and then inject voltages or currents directly into the relay, not on the transformer or not on the generators. I'm not talking about primary injection. So let's first talk about through fault or an external fault. What should happen for a differential protection when the relay sees a fault external to the CT protected area or zone of protection? When I supply a nominal current or a value that represents external fault, the relay should not operate because it is not within that zone. So if I inject certain voltages and currents into the relay, which represents a fault outside of the protected zone or a nominal operating condition, the relay should not operate. So that is your sensitivity and also your selectivity actually. So that actually is your selectivity function. So the relay should operate if there is a fault within the protected zone. The relay should not operate if there is a fault outside of its protected zone. That is what you're testing by injecting voltages and currents and doing a through fault test. So the next test that you might do is your pickup test. When you're doing a pickup test, you are actually verifying the minimum operating current of the differential relay for an internal fault. Either that internal fault could be a line to line or line to neutral. So you're verifying whether the relay picks up at what it is set to. So if the set value is 2 amps, whether that relay is picking that or not. Sometimes it may also require a pre-fault value before you can ramp up the value, ramp up the current and see where it picks up. Talking about the timing test on a differential, it is very important to do to validate your time coordination studies. So timing test you will perform to make sure that the expected trip time of the internal expected trip time of the relay for internal faults are right. So when you do the pickup test, you would do the pickup test on winding 1 and also on winding 2. The pickup value should fall within the tolerance as mentioned by the relay manufacturers. That I have seen so far, the tolerance values of the pickup test or the tolerance value will be somewhere around 3 to 5%, even for electromechanical or microprocessor relays. Now let's talk about doing a slope test, or also known as the characteristic test. So what are you verifying in that? You're verifying whether the bias equations and also the slope are according to what the relay is set to. And you have to make sure that you're testing at different restraint current values that validates the protection for its sensitivity. So depending upon the fault current that you're injecting, the relay should operate based on the slope value and also the restraint equation. So I have provided some of the restraint equations and from different manufacturers. So when you do a characteristic test on it, you can choose points at various you can choose at various points of the slope and make sure the relay operates within the specified tolerance. I just want to remind in this part, anything above this red line is the no operation zone. Oh, sorry, this is the operation zone. So the relay should operate within this or above this red line or within this tolerance range. The relay should not operate for the restraint region. So this will be a restraint region and the relay should not operate. Harmonic block test. We've discussed about this, and especially during the inrush condition. So how do you actually do a harmonic block test? So the way you do is, or the reason for you to do it is to verify the blocking logic of the relay. When there is a second harmonic or fourth harmonic or both present in the system. So what you actually do is you supply a fundamental current into the relay which is more than the pickup value. What should the relay do for that? The relay should pick up and it should trip. Now when you also supply the second harmonic or the fourth harmonic or third harmonic or the fifth harmonic, depending upon what test are you doing. If you're doing an overexcitation test, then you would pretty much supply the odd harmonics, which is 3 and 5. If you are doing the magnetizing inrush, you would do even harmonic, which is 2 and 4. So you would supply a fundamental current, which is above the pickup to make the relay operate. And you will, after you make the relay operate, you will start supplying or you will start ramping the harmonic content of the waveform. And after if the value goes beyond a threshold, then the relay should block the relay operation. So the relay should not operate if there is a specific amount of harmonic current present in the waveform. So that's how you would do a harmonic block test. Again, you would do it on a winding basis. If you have a 3-winding transformer and you have to do the harmonic test on that, so you would do it winding 1, winding 2, and winding 3 as well, separately. Harmonic shot test is, this is pretty much a go no go test. What you would do is pretty similar to what you would do on a harmonic block test as well. Your fundamental current will be higher than the pickup, and you would inject your harmonic waveform less than the tolerance, the relay should operate. If you inject a harmonic value more than the tolerance, then the relay should block. So you will verify that. So the relay operates for a harmonic value less than the settings. The relay restrains itself from operation for a harmonic value higher than its settings. So you're verifying, it's pretty much a shot test. As I mentioned before, you have to do it on individual windings as well. Having said that, the SMRT feature offered by Megger provides, the SMRT46D provides 4 voltages and 6 currents. It has convertible voltage and convertible voltage channels that you can convert into current channels, so you can test either the single phase or the 3-phase differential protection scheme at the same time. If you are doing bus differential and more complex procedures like that, then the SMRT410 might be an ideal option because it has 4 voltages and 10 current channels, pretty much will be sufficient to test one phase at a time on the bus differential as well. Along with the hardware features of the SMRT, the RTMS, that's the software that controls the SMRT, also provides a lot of features. We have automated modules for three-phase differential protection, and we have segregated that into transformer, generator, and motor protection, because transformer requires certain calculations, and generators require certain calculations, and motor differential requires certain calculations. So we have specific automated modules for transformers, generators, and motors for three-phase differential protection. On top of that, all the tests that I mentioned before, like doing a true fault test or an external fault, doing a timing test or a pickup test, or the slope test, and the harmonic block or restraint test. You can do all these things which are automated as well. So we have built-in curves along with the slopes. We have built-in curves for almost all the relays available in the market, the timing curves, so you can verify your time coordination studies. Along with that, the most very important thing here is you have a centralized control when you do a daisy chain of multiple units. You can daisy chain up to 32 current channels. If you want to test a scheme, if you want to do a scheme test on a bus differential, which involves about 6 feeders, so you need 18 currents to test. So pretty much you can daisy chain up to 32 channels to test your bus differential scheme. So in summary, we talked about the fundamentals of differential protection. We did cover about the percentage differential and the high impedance differential. Percentage is where you incorporate slope, and the high impedance is where you monitor the voltage. Protecting your equipment is very important because any fault can damage the equipment permanently. So your differential function is a primary protection function for most of these equipments in your power system, or most of your assets. This differential function is highly selective and also sensitive. It operates for all the faults within the protected zone, and it restrains from operation, or it will not operate for any faults outside of the protected zone. Having said that, there are many factors which affects the normal operation of your differential function. We talked about most of these stuff. You have CT mismatch, you have CT saturation, you have switching currents, magnetizing inrush currents, the overexcitation condition, or your zero sequence components. Having said that, we do offer different ideas for different challenges, and try to overcome those challenges in the field. This pretty much, these are the references for the presentation. I'll be more than happy to share the other information as well if you need. If you have any questions, if it is not answered during this presentation, shoot me an email. I will try to answer that as quick as I can.
Awesome. Thank you, Vijay. You did a great job. At this time, the presentation part of the webinar is officially concluded. We're going to go ahead and start our Q&A session. We have a lot of questions that have come through, so we're going to take about 15 minutes, as much as we can, to go through as many questions as possible. If you do have further questions, like Vijay said, you can email him, or there's the Q&A box on the right-hand side in the GoToWebinar screen. You can just ask a question there. We would also greatly appreciate if you're leaving the call, and at the end of the call, if you would take just a couple of minutes to provide your feedback. That way we can continue to improve on our future webinars. And as we stated before, a copy of the presentation will be emailed to everyone in the next few days, along with the video recording, so you'll get both. And you'll also be able to view any video recordings of previous webinars and our upcoming webinar schedule on our website. It's at us.megger.com. /webinars. Today, we do have a guest panelist to help with our Q&A session. His name is Clay Turney. He's one of Megger's applications engineers. He also works with BJ. So let's go ahead and get to your questions. Like I said, we have a ton. So I'm going to go ahead and toss this first one to Clay. This question comes in from Joaquin. He asks, how often does a bus differential occur?
Okay, can you hear me all right, sir?
Yeah. Loud and clear.
Okay, so for bus differential faults are extremely rare, and probably you won't see but a handful in your career, but the potential for the extremely high damaging current is extreme. So they have to be taken extremely seriously, because if a bus differential fault is not cleared, it would be extremely damaging on the system. So it's highly advisable to implement bus differential protection and hope you never need it. I think that solves that one.
Perfect. And then I've got another question. I'll direct this at you as well, Clay, from Joaquin. He asks, compare other types of faults with the differential.
Okay. The key to the differential faults is it's an internal fault. When we say internal, it's between the two CTs that contribute to the relay. So that's how you detect a fault inside a transformer, as opposed to just as an overload that would detect a fault in just one direction, that current's flowing through it. The cancellation of the currents help you restrain through faults, line faults, or downstream faults from operating the transformer differential. But any faults between the CTs, they sum together, you have a very high amount of operating current, and you can clear it for that internal fault. Okay.
Perfect. Okay, VJ, I'm going to toss this one to you. The question comes from Nick. He asks, if you have an external ground fault in series with the equipment current, will it raise at the fault? So why will it not raise through the equipment? Did that come through okay?
Okay, I will not raise through the equipment. If you have an external ground fault in series with the equipment, current will raise. Okay, hold on. I'm trying to understand the question.
Well, and if need be, we can certainly answer this offline. We've got Nick's contact info.
Okay, sure.
If you'd rather do that. Okay, Clay, I've got another one for you. Christian asks, please go over the slope diagram again. I believe that was on slide 14, VJ.
Okay, before I go over the slope diagram again, I want to give a background on this slide first. So you have an equipment, and the current flows through the equipment. If there is an internal fault, then internal fault within that equipment or within that protected zone, then pretty much the current flow will be towards the fault, right? So the CT will see that current, and it will generate the current on the secondary side in this direction, as I mentioned here. And the current flows through the restraint coils and the operating coil in this case. So these are the restraint coils, and this is your operating coil. Typically, if I take a graph, or if I draw a graph between IOP, which is your operating current, and IR, which is your restraint current, the restraint current is calculated different ways. Each manufacturer calculates the restraint current differently. As I mentioned, you can take the minimum of these two currents or the maximum of these two currents, or you can also do an average of the magnitude or a vectorial average as well. So there are different types of calculating the IR, but where is that from? That's from the restraint current here. So with that, in this case here, you have a 50% slope, let's say. So what does that mean to us? For the relay to operate, in this case, I don't know whether I can, okay, I think I can draw here. So in this particular point, right, so I need some amount of restraint current and some amount of operating current. For the relay to operate, the I operation in this case, IOP, should be greater than 50% of whatever the IR should be. Okay? In this point, it will be the same case, but instead of 50%, it will be 40%. Same thing here as well, 25% instead of 50%. So for the relay to operate, the IOP, which is from here, so the IOP should be 50% of whatever the calculation is on this restraint current. So that's what is mentioned here. Okay. Instead of having just one slope, like, hey, I want to operate every single time. How do I get rid of this? So instead of having one particular slope, so if I have one particular slope, what I actually am saying is, if I have IOP 50% of IR, a calculated value, then I will operate. It will not work all the time, because especially in this region where the CT mismatches are more pronounced, you need more protection here. So you need to have more IOP, even though you have IR, restraint current, which is less. Now, this might be a regular operating condition, so you can have your 25% or 40% or 50%. Well, typically anywhere between 10 to 25%. Okay? So you can have about 20%, let's say. But as you go higher, you cannot have 20% all the time. Okay? The reason for that is when there is a close-in fault, your current magnitude will be really high. So if your current magnitude is really high, your restraint current and your operating current will also be high. So you might end up in this region for an external fault, and your relay will operate for an external fault, which should not be the case. So in order for you to protect against CT saturation on high magnitudes, you want to protect it more. So again, decreasing the sensitivity of the function. Here you're increasing the sensitivity, and in this part you're decreasing the sensitivity. So you'll have a slope higher than the slope number 1. Okay? And if you look at overall, so you'll have multiple slopes for the differential function. So that's why, or this is the basic for using multiple slope on a percentage differential. I hope that answered the question.
Perfect. Okay, we've got time for maybe 2 more questions. This one I'm going to toss at Clay. The question is, can you use only one CT for a differential in a transformer?
Differential and transformer. Oh, sorry. Go ahead, Clay.
Okay, one of the keys of differential is you are taking what goes in must come out. So if you only have one CT, you can only see one side of the picture. There's nothing to compare to see a difference. So it is impossible to really implement one CT in a differential scheme, in any scheme. Now, it may be possible to use one CT out of a transformer and the other CT out of a downstream breaker or some scheme like that. But every differential scheme must have 2. CT contributions.
Okay.
That answers that one?
Let's see. Perfect. And then another one for you, Clay. Can you please explain in detail the DC offset component?
Okay, so that's probably a characteristic of a transformer inrush. You have an inrush into the core of a transformer. It's the flux state of that transformer is going to rebalance when the AC is applied to it, and you're going to have a DC component for some short period of time, probably in the seconds, when half a second to 2 or 3 seconds, depending on size and type of transformer. So the DC component is going to be a offset or a DC offset of the AC waveform during the inrush on the transformer, and that's going to die out pretty fast as the flux builds up in the core of the transformer. That DC component will die out over time. I hope that answers his question.
Okay. The next one, I'll leave this open to Clay or VJ. Mike asks, how to address CT connections and possible resonance. I'm sorry?
Ferroresonance.
Ferroresonance, thank you, issues.
Okay, ferroresonance is a typical overvoltage phenomenon from older schemes, especially with wire-wound PTs. The inductance of those PTs overvoltaging. CT connections may not implement your ferroresonance that much. It's usually going to come around from your potential sources in your substation. So if you do have a ferroresonance issue, it's just you're going to have a overvoltage due to those impedances matching up. So CT connections and ferroresonance issues. So I guess I'm maybe not sure if he has a particular question on that, but I hope that solves the question.
Okay, and if not, Mike, feel free to again put in the Q&A section if you've got more that you need to know about that, or like we said, you can email VJ. I've got one more question, and again, this will be for Clay or VJ. Ramesh asked, I'm sorry?
There's one question about defined masking.
Okay, go ahead and do that one then.
So there's one question about what is masking and what does the masking mean. Typically, the microprocessor relays have multiple logics enabled. You can have the relay operate for overcurrent function. You can have relay operate for distance function, differential function, negative sequence overcurrent, or under voltage, over voltage, under frequency, over frequency. You can have different protection functions enabled in a microprocessor relay. And when you're testing a microprocessor relay, let's say the pickup of the instantaneous function is 10 amps, and you also have a time overcurrent which is 5 amps, set at 5 amps. You have distance function enabled at 2.3 ohms. When I inject certain voltages and currents, how do I know that the relay operated for whatever fault that I'm trying to test? I may not know that exactly. The relay could have operated for a distance function when I'm trying to test overcurrent function. So what I do is I disable the distance function tripping the relay. So I am masking the effect of distance function when I am testing the overcurrent function. So that is called masking. So you are not allowing a certain protection function to operate when you're testing a different element. So that is what I talked about, element testing versus scheme testing. Do you want to change the output context of the relay, or do you don't want to change the output context? There are two schools of thoughts again, and it is up to the utility or the person who is testing it whether to do a scheme test or to mask the other elements, which is also called as the element test. Element test is much easier to do because you can write a program, automated program to do an element test. Scheme testing, automating a scheme testing requires a lot of knowledge and also a deep understanding of the scheme itself.
Perfect. Thank you so much, Vijay. It looks like we're all out of time for the Q&A session. We apologize if we didn't get to your question today. Like I said, we had a ton of questions and we still have more. We will try to follow up with those offline. Thank you all for attending so much. And we hope to see you again at our next webinar. It'll be on November 17th at 10 o'clock a.m. Central Standard Time. It's titled The Evolution of Insulation Resistance Testing, and it's going to be presented by Jeff Jowett. He's Megger's Senior Applications Engineer. And again, please remember to fill out the survey at the end of the call. The survey also includes a field for you to request a quote or demo if you're interested. And thank you all again for attending, and have a great weekend.
Thanks, everyone. Appreciate it.